This is Musaurus and I am doing my B from Mehran University. Let's study colligative property, which is elevation in boiling point. So let's take a pure solvent. This particular solvent would have a specific temperature as its boiling point. So the definition of boiling point is that temperature wherein the vapor pressure of the solvent would be equal to the external pressure, which in our case is 1 atmosphere. So boiling point will be equal to external pressure equal vapor pressure. So it has been experimentally observed on adding non-volatile solute boiling point increases. So why is this happening? Now let's explain why this elevation of boiling point occurs. As we keep adding a non-volatile solute to the volatile solvent, there is a relative lowering of vapor pressure. Now, because the vapor pressure of solution has gone down, the boiling point becomes higher. Why? Because boiling point is that particular temperature where vapor pressure of the solution equal to atmospheric pressure. Because vapor pressure has gone down, you would require a higher temperature to achieve the state where vapor pressure of the solution becomes equal to the atmospheric pressure. Because of this, boiling point of the solution goes higher, and that is why this colligative property is called as elevation in boiling point. Furthermore, this elevation in boiling point is directly proportional to the amount of solute that is being added to the solution. Let's explain this phenomena graphically. Let's plot the graph between vapor pressure and temperature. So for a pure solvent, the relation between vapor pressure and temperature would be something like this, the graph xy. Note that as the temperature is increasing, the vapor pressure of pure solvents, which is a liquid, is also increasing. Note that over here, point A, A is a boiling point where vapor pressure of pure solvent is equal to 180 atm. Now I added a non-volatile solute. Because of this, the graph for the new solution shifts to the graph CD. CD here B would be the boiling point. Meaning at point B is where we get vapor pressure of the solution to be equal to the atmospheric pressure. Now let me explain what is happening here. Because we are adding a non-volatile solute, the vapor pressure at that particular temperature, which is P0, is going low. So the vapor pressure clearly has gone down. Because of this, again, to reach that particular state where vapor pressure of the solution becomes equal to the atmospheric pressure, you will have to boil that solution higher or take that solution to a higher temperature. So this change in boiling point is called as delta TB. So delta TB has been experimentally proved to be directly proportional to the molality, which is the concentration of the solution. Delta B is directly proportional to the where Kb is elevation constant or molar elevation constant. So guys, this is delta B is equal to Kb, and this is very important derivation. And here Kb is also called ebullioscopic constant. Now let's study the different ways in which this particular formula can be applied in case of problems. So delta TB is equal to Kb into M. So substituting delta TB is equal to Kb M by WB divided by MWB into WA whole into 1000. So it would be 1000 into Kb WB divided by MWB into WA. So let's understand what the application of this particular colligative property. If we know the elevation and boiling point, and if we know the weights of the solute as well as the solvents, then we can easily calculate the molecular weight of the solute. So here Kb is equal to RT square by LV into 1000. So here R is gas constant, T is temperature, and LV is latent heat of vaporization. After looking at elevation and boiling point, let's move to the next colligative property, which is depression and freezing point. First of all, guys, what is freezing point? Freezing point is that temperature wherein the solid state and the liquid state of a particular substance have same vapor pressure. Now, in this context, in the earlier colligative property, we learned that we add a non-volatile solute to a volatile solvent, the vapor pressure decreases. As vapor pressure of the solution decreases, the temperature required in order to get the vapor pressure of the solid and liquid state to be equal also reduce. Consequently, there is a decrease or depression in freezing point. It has been experimentally observed that depression in freezing point delta TF is directly proportional to the amount of non-volatile solute that is being added. In this context, delta TF is equal to Kf into M. So there Kf is freezing point depression constant and Kf is also cryoscopic constant. Note that this is a colligative property because depression in freezing point, the quantum of depression in freezing point is directly proportional to the amount of non-volatile solute that is solute added to the solution. Let's explain this in a graph. The graph consists of plotting Vp against temperature. What we see is the curve for the solvent in the liquid state. This is the curve for the solid in the solid state. Now point B is now over here where frozen solvent, graph of frozen solid and liquid solvent is meeting. So let's say this is a point B. Let's assume that the temperature to be T naught because we are adding a non-volatile solute to the solution. The graph goes down, it shifts to the graph of new solution. On adding non-volatile solute, this graph will look like this, the graph of this solution. So it means vapor pressure has gone down and we will need to give lower temperature than before adding a non-volatile solute. So this as we mentioned earlier, this colligative property can be used to determine the molecular weight of the unknown solute. And here Kf is equal to RT square by LF into 1000. Here LF is latent heat of fusion.